Hello and welcome to this class, the application of related rays, the telescope and the airplane. If a variable depends on time t, then its derivative dy dt is called a time rate of change. Of course, if y measures distance, then this time rate of change is also called velocity. We are interested in a wide variety of time rates. The rate at which water is flowing into a bucket, the rate at which the area of an oil spill is growing, the rate at which the value of a piece of real estate is increasing, and so on. If y is given explicitly in terms of t, the problem is quite simple. We just differentiate and then evaluate the derivative at the required time. It may be that, in place of knowing y explicitly in terms of t, we know a relationship that connects y and another variable x, and that we also know something about dx dt. We may still be able to find the derivative of y with respect to t, since the derivative and the derivative of x with respect to t are related rates. This view usually requires implicit differentiation. The following methods are suggested for solving a related rates problem. Step 1. Let t denote the elapsed time. Draw a diagram that is valid for all t is positive. Label those quantities whose values do not change as t increase with their given constant values. Assign letters to the quantities that vary with t, and label the appropriate part of the figure with these variables. Step 2. State what is given about the variable and what information is wanted about them. This information will be in the form of derivative with respect to t. Step 3. Relate the variables by writing an equation that is valid at all times t positive, not just at some particular instant. Step 4. Differentiate the equation found in step 3 implicitly with respect to t. The resulting equation containing derivatives with respect to t is true for all t is positive. Step 5. At this point and not earlier, substitute in the equation found in step 4 all data that valid at the particular instant for which the answer to the problem is required. Solve for the desired derivative. Now let's see one example. Jack, could you read this problem for me?
Example 1. A woman standing on a cliff is watching a motorboat through a telescope as the boat approaches the shoreline directly below her. If the telescope is 250 feet above the water level, and if the boat is approaching at 20 feet per second, at what rate is the angle of the telescope changing when the boat is 250 feet from the shore?
All right, very good. Thank you. Now let's solve it. Just use the steps that we talked about earlier. First, we draw a figure and introduce variable x and theta as shown. Second, we are given that the derivative of x with respect to t is minus 20. The sign is negative because x is decreasing. Step 3. From trigonometry, we know tangent theta is x over 250. Step 4. We differentiate implicitly using the fact that the derivative of tangent theta is secant squared theta. This gives secant squared theta d theta dt is equal to 1 over 250 dx dt. All right, we are almost done. Step 5. At the instant when x is 250, theta is pi over 4, and secant theta squared is equal to secant squared pi over 4, and it's 2. Thus, we have 2 d theta dt is 1 over 250 times minus 20. So we get that the derivative of theta with respect to t is minus 0.04. So we get the answer that the angle is changing at minus 0.04 radian per second. The negative sign shows that theta is decreasing with time. All right, now let's see the next example. Is there anybody who can read this problem for me? Jordanson, please.
Example 2. An airplane flying north at 640 miles per hour passes over a certain town at noon. A second airplane going east at 600 miles per hour is directly over the same town 15 minutes later. If the airplanes are flying at the same altitude, how fast will they be separating at 1:15 p.m.?
Thank you, Jordanson. So this is a problem about 2 airplanes. One airplane flying to the north, then another one flying to the east. So the question is, how fast will they be separating at a certain time? Now let's solve it. Again, we follow the steps. So step 1, let t denote the number of hours after 12:15 p.m. Y, the distance in miles flown by the northbound airplane after 12:15 p.m. X, the distance flown by the eastbound airplane after 12:15 p.m. And S, the distance between the airplanes. In the 15 minutes from noon to 12:15 p.m., the northbound airplane will have flown 640 over 4 and is equal to 160 miles. So the distance from the town to the northbound airplane at time t will be y plus 160. Step 2. We are given that for all t positive, that the derivative of y with respect to t is 640, and the derivative of x with respect to t is 600. We want to know the derivative of x with respect to t at t is equal to 1. That is at 1:15 p.m. Step 3. By the Pythagorean theorem, we know x squared is equal to x squared plus y plus 160 squared. Step 4. Differentiating implicitly with respect to t and using the chain rule. Then we have 2x times ds dt is equal to 2x dx dt times 2y plus 160 dy dt. Always simplify it like this. Then step 5. For all t is positive, dy dt is 640 and dx dt is 600, well, at the particular instant t equals 1, x equals 600, y equals 640. And s is this part, according to the Pythagorean theorem. So s is 1000. When we substitute their data in the equation of step 4, we obtain that 1000 ds dt is equal to this part, from which we can get the derivative of s with respect to t is 872. At 1:15 p.m., the airplanes are separating at 872 miles per hour. All right, that's all for this section. See you next time.